Welcome to my YouTube channel. Today is our lecture number 4 of the Linear Algebra course. In this lecture, I first describe a theorem which states that every matrix is row equivalent to one and only one reduced echelon matrix. It means that irrespective of the sequence of row operations that you perform, at the end, the reduced echelon matrix that you will receive is going to be unique. Now we continue our discussion about the systems of linear equations, and today we discuss the homogeneous case. And what are homogeneous equations? On the right hand side, that constant is 0. For example, in this equation on the right hand side this is 0. Similarly, in this equation on the right hand side I have 0. So combining these two equations into a system, the system that I receive is going to be termed as a homogeneous system of linear equations. And if I plot them, what do I notice? That this point 0, 0 is always a solution of this homogeneous system. Okay. So in general, if I have a homogeneous system, x equal to 0, since for the vector x equal to 0, the system is satisfied, hence the system is always consistent. It means that homogeneous systems are always consistent, and the solution x equal to 0 is called the trivial solution of the homogeneous system. Since this solution is readily available, hence we are interested in other solutions where x is different from 0. So if ax equal to 0 has infinitely many solutions, then the solutions other than the trivial solutions are called the non-trivial solutions and can be computed as discussed for the system Ax equals b. So if I have a homogeneous system, the first thing that I have, that homogeneous systems are always consistent. If they have a unique solution, then the unique solution for homogeneous system is termed as the trivial solution. If this homogeneous system has infinitely many solutions, they can be computed as discussed for Ax equals b for infinitely many solutions. And we will see that we are most of the time interested in non-trivial solutions. For example, at the end of today's lecture, we will have an example where we will be interested in non-trivial solution of the linear system. Similarly, in future, we will need them in transformations, in vector spaces, and in eigenvalue problems. So additionally, if I have a homogeneous system, we know that for general linear system, once we had this vector b over here instead of 0, so in augmented matrix what we were doing, that the rightmost column were the entries of this vector b. Since in this case I have zeros, hence in AB we can always omit the rightmost column for reducing the matrix into echelon form, because performing operations on zeros will never change the entries. So for example, determine if the system has non-trivial solutions. So I have these three planes and I am looking for non-trivial solutions of this system. So what I do, I omit the rightmost column because it consists of zeros, so I omit it and I just take the matrix of the coefficients 3, 5, minus 4, minus 3, minus 2, 4, 6, 1 and minus 8, and I reduce this matrix into a reduced echelon form matrix. I hope you can follow these sequence of operations. So here I notice that this is a pivot entry, this is a pivot entry. Since this is a row of zeros, hence there is no pivot entry in this row, and this pivot entry corresponds to the variable x1, this corresponds to the variable x2, hence x1 and x2 are my basic variables and x3 is a free variable, and hence the system has non-trivial solutions which can be computed as x2 is equal to 0. From this row I have x2 equals 0, and from this row I will have x1 minus 4 by 3 x3 equals 0, and hence I can compute x1 as 4 by 3 x3, resulting the non-trivial solution is x3 times 4 by 3 0 1. Since x3 is a free variable, so assigning any value to x3 will result into a solution of this homogeneous system. Now we discuss a very simple application of the homogeneous linear system. So we consider a very simple economy where an economy consists of coal, electric and steel sectors, and the output of each sector is distributed among various sectors as given in the table, where the entries in a column represent the fractional part of a sector's total output. So the table is available here. I have coal, electric and steel, and it is distributed that coal utilizes 0.0 or 0% for itself, 0.6% is utilized by electric sector, and 0.4% is utilized by steel sector, and similarly the rest of the columns. So for example, the third column for instance says that the total output of the electric sector is divided as 40% to coal, 10% to electric and 50% to steel sector. Now the problem is, if possible, find equilibrium prices that make each sector's income match its expenditure. So we are interested in an equilibrium prices where each sector incomes match its expenditure. So what do? A sector looks down a column to see where its output goes. For example, here from this column I see that coal finds that 60% of its output goes to electric sector and 40% goes to steel sector, and additionally it looks across a row to see what it needs as an input. For instance, the coal receives and hence it must pay for 40%. For example, if I go here, the coal receives 40% from electric sector and 60% from steel sector, and hence I can summarize this as that 40% of the electric output and 60% of the steel output. Now represent the output of coal, electric and steel by PC, PE and PS respectively. To make the coal's income PC equal to its expenses, we must have that PC must be equal to 0.4 PE plus 0.6 PC, and similarly PE is equal to 0.1 PC plus 0.1 PE plus 0.2 PS, and this reduce, and similarly PS is equal to 0.4 PC plus 0.5 PE plus 0.2 PS. And if I simplify these equations, I have PC minus 0.4 PE minus 0.6 PC is equal to 0. Similarly, the rest of the two equations are summarized here. And the problem is to find equilibrium prices. Indeed, PC, PE and PS equal to 0, 0, 0 is equilibrium state, but that is not needed. Hence, we are interested in the non-trivial solutions of the system. So to compute that non-trivial system, I consider the matrix of its coefficients and I reduce that matrix into a reduced echelon form, and the reduced echelon form is given here. And here I see that PC and PE are basic variables and PS is a free variable, and the solution set is given by this thing, that PC, PE and PS are equal to 0.94 PS plus 0.85 PS and PS. I'm sorry, not plus, it is 0.94 PS, 0.85 PS and PS, which is equal to PS times this thing, and hence assigning any non-negative value to PS will result into the equilibrium values of the system. That's it for today. Thank you.